Welcome to the Explainer. So, if you've ever wondered how modern AI applications magically pull up the exact quote from your proprietary company documents, or how they somehow know about niche events that literally just happened yesterday, well, you're in the right place. Today, we're totally demystifying RAG. Let's get right into it.
So how exactly does an AI know your private company data? Because here's the thing, large language models are absolutely incredible writers and reasoners, right? But they are terrible mind readers. Sure, they've been trained on a massive chunk of the open internet, but they definitely haven't read your company's internal HR handbook or your latest financial PDFs.
And that brings us to the real issue. AI has some pretty major limitations right out of the box. It doesn't inherently know your private data. Plus, it lacks fresh, real-time info, meaning it's stuck knowing the world exactly as it existed up until its training cutoff date. On top of that, if you ask it a super specific question, it might just guess. It generates an ungrounded answer, which we often call a hallucination. And even if a model could magically hold thousands of documents in its memory, reading through massive collections every single time you ask a basic question, yet that's just incredibly inefficient.
So here's our roadmap for today. 1. What is RAG? 2. The ingestion phase. 3. The query phase. 4. RAG versus fine-tuning. And 5. Perfecting your RAG system.
What is RAG? The solution to AI's knowledge gap.
To really bridge the gap between a highly capable AI brain and your private facts, we need a solid mental model. Think of the AI as the writer, your database as the library, and RAG as the incredibly helpful librarian sitting right between them. When you ask a question, that librarian sprints into the library, grabs the exact pages you need, and hands them to the writer so they can craft a perfect factual response based exclusively on those pages. Formally, we call this retrieval-augmented generation. And honestly, the name tells you exactly what it does. Instead of expecting the LLM to have magically memorized everything in the universe, we retrieve the relevant facts first, augment the AI's prompt with those facts, and then let it generate the answer. We're literally handing it the source material the exact moment you ask the question, so it doesn't have to guess.
Section 2. The ingestion phase. Stocking the library.
Okay, so before our librarian can fetch anything, we actually have to get the information into the library in the first place, right? We follow 4 distinct steps to do this systematically. Imagine you're building an app where users can ask questions about a massive machine learning textbook. First, your application loads that source document. Second, it extracts the raw text and cleans it up. Third, it splits that text into smaller chunks. And finally, it converts those chunks into numerical embeddings.
Let's zoom in on that third step for a second. We simply cannot overwhelm the model's context window, so we use a process called chunking to break large files down into bite-sized pieces. Trying to feed an entire 100-page textbook to an AI all at once for a single question, it's just not going to work. So we divide it up into chunks of several hundred tokens, and we usually leave a little overlap between neighboring chunks so we don't accidentally chop a crucial sentence right in half.
That brings us to step 4, converting those text chunks into numerical embeddings. Now, an embedding is really just a mathematical representation of what the text actually means. Think about these two phrases. How does JWT authentication work versus explain JSON Web Token authentication? Notice how, even though the wording between them is entirely different, the mathematical meaning remains almost identical in vector space. This is a complete superpower. It means the system actually understands semantic meaning, not just exact keyword matches. Once we have those mathematical chunks, we obviously have to store them somewhere searchable. We use a vector database for this. You've probably heard of popular tools like Pinecone, Qdrant, Weaviate, Milvus, Chroma, or pgvector. But here's the kicker. It's not just the math being stored. A truly great system stores the chunk, its embedding, and crucial metadata. Things like the document name, the exact page number, or even user ID permissions. This ensures your librarian only hands out books that the specific user is actually allowed to read.
Section 3. The query phase. Asking the librarian. All right, now that our library is fully stocked, let's see what happens when a user actually asks a question. This is the query phase, an elegant 4-step process where our librarian finds the most relevant chunks and hands them to the AI writer. Say a user asks, "What is two-phase locking?" The application immediately converts that question into an embedding using the exact same model we used during ingestion. Then, it does a similarity search in the vector database to retrieve the chunks that are mathematically closest to the question. It completely bypasses all the unrelated stuff and pulls exactly what is needed.
And the augmentation part, that's where we literally insert those retrieved document chunks directly into the prompt, right alongside the user's question. We give the system specific instructions like answer using the provided context. We paste the retrieved chunks right in there, then we append the user's question. Finally, in the generation step, the LLM reads the whole package and generates a highly accurate, grounded answer. It completely avoids relying solely on its internal pre-trained memory.
Section 4. RAG versus fine-tuning, choosing the right tool.
You know, there's a huge misconception out there that to teach an AI new facts, you have to retrain the entire model. Actually, RAG and fine-tuning solve completely different problems. The absolute biggest takeaway here is that RAG does not retrain the LLM. You want to use RAG when your main problem is accessing external, private, or constantly changing knowledge at query time. On the flip side, use fine-tuning when you actually need to fundamentally change the AI's behavior, tweak its speaking style, change its formatting, or teach it task-specific patterns by training it on examples. They serve totally different purposes. Though to be fair, in advanced systems, they can absolutely be combined.
Section 5. Perfecting your RAG system, fixing the pitfalls.
Okay, so while RAG is incredibly powerful, it definitely isn't magic. Building a production-ready system means you're going to navigate some frustrating roadblocks. You might run into bad chunking, where you accidentally split important information right down the middle, meaning the retriever just misses it entirely. Or you might suffer from poor similarity search if your embeddings are weak. And if you retrieve way too much irrelevant context, you'll just confuse the model, which leads right back to those hallucinations we were trying to avoid in the first place. Plus, missing metadata makes it impossible to filter by permissions, and if your documents go stale, well, your AI will confidently give out completely outdated answers.
So, how do we fix these issues? Well, you need to experiment continuously with your chunk sizes and overlap. Try using hybrid search, which combines traditional keyword matching with semantic vector search to get the absolute best of both worlds. You should also consider using a re-ranker to double-check the relevance of the retrieved chunks before they ever hit the AI. Keep your context window highly focused, and definitely always add source citations so your users know exactly which document and which page the answer came from. Finally, make sure to log your failed questions so you can continuously evaluate and improve your pipeline over time. I want to leave you with this provocative thought. Today, RAG is basically a straight line from a question to a database to an answer. But as workflow frameworks and intelligent agents like LangGraph get even smarter, gaining the ability to decide exactly when to retrieve data, which tools to call, and when to ask humans for approval, the librarian is essentially becoming an entire research department. As these orchestrators evolve, how will you organize your private data to empower the truly intelligent applications of tomorrow?